Assalamualaikum warahmatullahi ta'ala wabarakatuh. And very good morning. First of all, my name is Muhammad Her. At present, I am one of the committee member for MNATD, Marine and Naval Architect Technical Division. And I will be the moderator for the session for this morning. I wish to thank to everybody for your time, making yourself available, attending and providing continuous support to all activities being organized or been organized by IEM. I know that for this week or for today in particular, we may be busy attending a lot of open houses, but you still have time to attend the specific technical talk for this morning. Again, today we have another session of technical talk organized by MATD, and Alhamdulillah, this morning we managed to bring a special speaker. I would consider OTAI in UTM, which is Professor Dr. Adi Maimun. He will be delivering a very specific subject. The title is Reducing Hull Resistance Using Air Injection for LNG Vessel with Free Ballast System. Yeah, I think this is very interesting subject. By the fact that LNG vessel is heavily utilized in marine industry and as well as oil and gas industry. Very quick background on our speaker, Professor Adi Maimun. As I mentioned previously, one of the OTAI that we regard, especially within the marine industry. At present, Professor Dr. Adi Maimun is currently serving as a professor in naval architect in Faculty of Mechanical Engineering, UTM Skudai. His specialization mainly in the field of marine vehicle and structural dynamics using CFD, FEA, AIS, adopting time domain simulation, and as well as he is performing on experimental work as well. He had published, I would say, more than 100 international papers related to his area. At this moment, Dr. Hadi or Professor Hadi is currently a fellow member for Royal Institute of Naval Architect and as well as a chartered engineer for United Kingdom. Previously, he had served in numerous committee members such as RINA, IMARES, and so on. Just very quick for all attendees here, just for reminder, please be reminded that during the session, all of you will be mute. And if you have any question, just please utilize the chat session at the bottom of your screen. Then I will forward this question to the speaker, as well as I will read the question for you as well. In terms of duration, typically we have 1 hour 30 minutes, more or less, for presentation and followed by Q&A. So we are targeting to complete our session today by approximately 1 p.m. today, right? So I hope it is clear. In terms of presentation material, yes, the presentation material is available. It can be downloaded at the end of the session. So that please stay tuned until the end of the session. Yeah, great. Prof, are you ready?
Okay.
Roger. Proceed. Thank you very much.
Okay, first thing, is my slide okay now? Can you see my first slide?
It's clear.
Okay.
It is clear. Fine. Please proceed. Thank you.
So, Assalamualaikum warahmatullahi wabarakatuh and a very good morning. Firstly, check my voice slide okay, yeah? Before I proceed.
Positive.
Okay. Thank you, Engineer Muhammad Her for being the moderator for this session. So I've been introduced here, and actually this topic is basically the research work that we've done a number of years. I think 3 years. It finished off with this PhD student graduating and working. Basically, as you see, the title is we are trying to reduce hull resistance. Yeah? But we didn't do we didn't intend to do reducing hull resistance first. what we did was we were working on having a free ballast system, for LNG vessel, because LNG vessel is a vessel that transport LNG. It goes, and then once he finish transporting, when he come back, basically the vessel is empty. So when they're empty, means the draft will be very low. And then usually what the captain need to do is to put ballast so that the draft increase, so that the propeller is submerged again. But the problem now is that there are problems with this carrying of this ballast water between ports, which according to IMO is not agreeable, because it transport of this marine organism can be harmful to other areas. So the idea is first to come up with this free ballast system. But however, when we do the free ballast system, we realize that it does increase significantly the hull resistance. So only then we start to consider how to reduce this hull resistance. So we came up with this using air injection, basically trying to introduce air to mix it with the water so that the water becomes less viscous, and with that we can reduce the the skin friction, which I will tell detail after this. Okay. So this is just an introduction. So that's what I was mentioning about the ballast water, not actually stabilized, just to increase the draft. You see, actually, when it's after discharging at the port, and then because I mentioned about the marine organism, supposed not to transport it. If the normal ballast system is that we have to find ways to kill the marine organism, and then there are a number of ways. So we opt for using a free ballast system, because there are a lot of ballast tank in the LNG vessel actually already existing. So this is under the IMO convention. We have to comply with the D1 and D2 standard. Okay, and then it must be implemented, I think by September 2022 and so on. So there are details that you see in the slide. So also, the IMO proposed on this reduction in sulfur and also reduction in emission, for the for reducing this greenhouse effect due to the emission. So basically, by 2050, we have to come up with something like some big reduction in the gas emission, of which Malaysia has ratified this IMO regulation. So we have to follow this, comply this by 2050. So that's the overview of the thing. So many studies have been done before for ballast water management and so on. So you can see this, some of the researchers' work by Cortinis 2005, Arai 2010, and Gode et al. 2012. So basically, Cortinis used the ballast water flow going into the bulbous bow and discharge at the stern of the ship. So we follow basically our continuous approach. Inlet outer opening at the bottom of the hull and appendages, also longitudinal tunnel throughout which the water flow through the double bottom. Okay, and then with that, with this free ballast, you see, actually we don't carry any water. Actually, the water just pass through the ballast tank. So it acts like you're ballasting it, but we don't retain water inside the ballast tank. Okay. So these are some again some detailed greenhouse gas emission for MARPOL Annex 6, Chapter 4. So basically, what we have to do, we have to comply with this regulation. They have this Energy Efficiency Index, Design Index (EEDI), and also the Ship Energy Efficiency Management Plan (SEMP). Okay, basically just to ensure that you you comply with this reduction of the, especially the emission. Okay, so EDI is basically at the design stage, and SEMP is more when you're operating the vessel to come up with this improved efficiency, so that the target is just to reduce the emission. So the regulation applied to all ships, 400 gross tonnage, so large vessel, medium and large vessel, start 2013 January. And then what is required is that the target is to reduce the total annual GHG emission by at least 50% by 2050 compared to 2008. So it's a big job, especially for the old vessel, new vessel, and even new vessel. You need to use technology. And I don't know whether it's good or bad. Malaysia has ratified this, so Malaysia has to comply with this now. Okay. So it involves with measures like reducing this methane, CH4, VOC emission, anything to do with low carbon, zero carbon fuel, and so on. Okay. Okay, so this is the previous study, as I mentioned just now. So this is the picture view of this method used by Courtinis, Arai, and Gaudet. So basically, we have this water coming through the hull. So we open the inlet from the bow, and the water pass through this ballast tank underneath. And after that, it will go out at the stern. Okay, there are some other things. These are some details of different method they use, but overall, that's the concept. That means the water just pass through the vessel from inlet to outlet. Okay, so the main thing here, we see that the effect on the resistance. You can see here, based on previous study. So you have this continuous got a 4.6% increase in resistance. Arai got 1% less. Okay, and then increment of 35% by Gaudet. That's quite a lot. So you can see that this method may not be positively looked by the operators, especially 35% means you have to increase the power by 35% to go at the same speed. And also not good for emission, is it? So this is the problem statement of the research. So we go for the ballast-free system. So with ballast-free system, you have increase in resistance. Basically, because of you increase the wetted surface area as the water pass through the pipes in the ballast tank. So with increase in surface area, you increase the friction because when the water slide against any surface, right, there is resistance introduced. So this lead to increased powering, and also with that, what you have is loss in ship efficiency. So as I mentioned, these are the people who go with this method, Courtinis and Gaudet and so on in Arai. So we need now to reduce the resistance somehow. Okay. So what they basically suggest is that introduction of this air, or air injection under the hull. So with that, we can reduce the resistance because of the mixture of air and water. Because air has a less density and also lesser viscosity as compared to water. So that will give the indication that it will reduce the resistance. So let's have a look at basically what we are talking here. I don't know whether I think maybe some of you are familiar. The naval architect is familiar, because resistance powering is very important for the naval architect, because it's in the contract of building the ship, So if the owner may may reject the vessel, delivery of the vessel if the powering is not comply. So that means in the contract, they specifically say how fast is the vessel, okay, and the powering requirement, especially with the EEDI, right? They have to check the what they call the fuel consumption, the emission, and so on. So that means at the design stage, you must design the vessel in such a way that you can achieve the contract powering requirement. So basically, the resistance is divided into three parts. Sorry, two parts. Two parts, or the number part. But the most important is the friction and the residual resistance. So friction comes from, as I mentioned, the friction between the water and the solid surface, or the metal surface of the hull, or the hull surface. Okay, and then residual resistance is based on this resistance due to the production of this wave, as the vessel fly through on the surface of the water. So we call it residual resistance. It's basically a two-phase flow. Okay, so these two resistance is not the same category, because the way naval architect predict the resistance, and they have this big tank, you see, and then they tow the ship models. Ship models are models that's smaller than the actual full scale, because we cannot make the full scales first. Okay, so we have to make the model first, and then you have to predict the powering based on the model scale. So that means whatever result you get from the model scale, you have to scale it up to the full scale. So with this, they have to scale up this resistance, or this ship resistance that they obtain through the experiment in the tank, so that they can scale it up to the full scale. So they divide into two here, friction and residual. So friction is more a function of Reynolds number, and residual resistance is basically based on Froude number. So the problem with our tank is that we cannot actually do experiment running on same Reynolds number. It's just not possible. You need a very high speed vessel, for that. I mean, high speed model to do that. And also we have problem with residual resistance. Resistance will be just too high. So the way we do is that we fix the experiment based on Froude number. Froude number. That means we can scale up the residual resistance effectively. No problem with this. But now how we deal with the frictional resistance? So the way they do is they use some sort of formula, based on flat plate resistance. So they got this formula for the coefficient of friction, as you've seen here. This is the International Towing Tank Conference, 1957. They already developed this relationship between the coefficient of the friction, based on Reynolds number. So we have to combine this. One part we do the experiment, the other part we based on this formula, and then we sum up this total resistance, give you this coefficient of total resistance. And from there, we can use this coefficient, and then we can scale it up to the full scale. Okay, so that will give us later on the total resistance. And once we know the total resistance, we can obtain the effective power, which is the total resistance times the velocity of the ship or the model. Okay, so there's some detailing of this coefficient, right? For the skin, or for the frictional resistance, we have some coefficient called 1 plus k. So k is to take into account the shape of the hull, because the formula is basically a flat plate formula. So we have to have some extra coefficient here to take into account the shape of the hull. Okay, and then with the residual resistance, no problem. Okay, it's basically due to the wave making, And then there's some resistance due to the appendage, like the rudder, propeller, and so on. Yeah? And then also resistance from the air. You know? But this is a bit, small resistance. So the major resistance is between the friction and the residual resistance. Okay, so this is the Reynolds number. So as you can see, the Reynolds number depends on the velocity, the length of the body, and also the kinematic viscosity. Or you can put in dynamic viscosity. Okay, about the same. Yeah? Okay, so this is the curve that they produce, right? So you can see that this is the log Reynolds number. So you can scale your result, yeah, from model to the ship. Yeah. So using this graph of this coefficient of friction, and then we can from there we can get the wave making resistance. We add up the two together, we can get the total resistance for the ship. Okay, so that's the basis of the analysis for the ship resistance, which is quite important in this case because we are dealing with predicting or obtaining the resistance or analyzing the resistance of the ship or the model. So another thing we have to look is this is quite common, especially in mechanical engineering. In engineering, this is called a boundary layer because of it's a real fluid we are talking about. So with real fluid, they have this boundary layer. Okay, for the basis of this boundary layer is that it will generate later on. We call it the shear stress that will result in the skin friction. So basically, for the model scale usually is in laminar boundary condition, and the full scale is usually in the turbulent boundary condition at higher Reynolds number. Yeah? And also we can predict the the thickness of this boundary layer using some formula. Okay. So as I mentioned just now, with this boundary layer, you will end up with shear stress, because shear stress is a function of this boundary layer, and also with we call it, this is the dynamic viscosity. It's related to the kinematic viscosity by the the density of the fluid. Okay, so that means if you were to have depending on this profile of your boundary layer, then your shear stress will be affected. Yeah. So what you have to do is try to decrease. To get a lower shear stress, you have to decrease your velocity profile. Yeah. And also, if you can decrease your properties of your fluid, like this is the dynamic viscosity, then you can reduce the shear stress. Once you can reduce the shear stress, you can reduce the skin friction, by this second formula. And usually what we do is that this is for local, right? For the overall length of the body, we just use we measure the fluid drag, using, say, for the ship, we just use, for the ship model, we use the towing tank, then divided by the wetted surface area. Okay. And then you can see here the wall shear stress in laminar flow and in turbulent flow. Usually for experiment, we try to avoid this area, the transition area. Okay, by checking our Reynolds number. So usually model scale is very close to the laminar area. But in full scale, it's actually in the turbulent flow. This is usually the dilemma we had, because then the flow is a bit different, because of this different laminar and turbulent. But if we know the Reynolds number, then we can do some correction for this laminar flow experiment. Want to scale up to turbulent flow. So this is the basis of the air lubrication technique. We have here three techniques. First, the MBDR, So MB means the, what do you call it, micro bubbles. You introduce bubble on the surface, on the surface of the body, so that you can change the properties of the fluid. So that means, as I mentioned, you can reduce the shear stress, and with that shear stress, we reduce the skin friction. Good. The second method is not using bubbles, but using air layers. That means more bubbles. You can introduce more bubbles so that it becomes a layer instead of bubbles. Okay. And then the third one is putting a cavity. So we put empty space so that the water doesn't touch the surface, Okay. So we inject air. So these two methods, second and third, is we inject air, Okay, it's one producing the layer, the other one producing a sort of a cavity. Okay, the top one also inject air, but not so much. It generate bubbles instead of air layer or cavity. And from the study, they found that it's more effective in reducing this is the resistance, percentage of reduction in resistance, decrease in resistance. The ALDR and ACDR method is more effective than using these micro bubbles. So nowadays, people are more focused with this ALDR and ACDR, but ACDR is practically the ship owner doesn't like to put a cavity underneath the hull. It means a lot of construction on this part. I think they're more towards this ALDR, because what you do is just put a pipe and then try to introduce the air layer to this pipe by injecting air into this. So this is more a method with more least intervention on the hull in terms of construction. Okay, here just showing the picture of this MBDR, ALDR, and ACDR method. What else? Okay, what is the difference? MBDR use less energy, because it just produce bubble, but it's not very effective. And then also the size of bubble also have a lot of impact. So you have to make sure the size of bubble is at the correct size for it to be effective. And usually effective more in the lower speed region, because the bubble, if you go fast, then the bubble just detach from the hull. So the middle one is the ALDR method. So I think this will be the most common method if you want to reduce the drag using air injection. But however, the disadvantage that the energy to produce, that means you need more of these compressors to generate the air layer. And the third one, the ACDR, as I mentioned, you need to modify the bottom hull, which most company, I think, owners wouldn't like this to be done, because you lose some space, and you have to make a hole underneath the hull, a big empty compartment. You see? Okay. And with the air layer, I think the important thing is the thickness of this air layer. So the correct thickness should be obtained. So from the previous research, you found out that it's between 4 to 8 millimeter of the thickness of the air layer. So this air layer, to produce the air layer, you need to produce the flow rate. This is by using compressors to inject air, and then that gives you the flow rate of the air. And then the thickness of the air layer depends on the width of the test model, how wide you want the air to cover underneath the hull. And also the flow of the vessel also affect this thickness of the layer. Okay, so the faster is the vessel, the more flow rate you need to maintain the thickness of the air layer. Okay, and then maybe some rough surface area, maybe you need a larger air influx of this. So this is to show you the effect on the frictional drag on the flat plate by considering using a sidewall. yeah, and then also with and without sidewall. So sidewall is basically to retain the air underneath the hull, you know. Okay, so without the sidewall, you can see here it's not very effective, yeah, in reducing the frictional drag. Okay, but once you put the sidewall, you have better effect, yeah, from the air layer. Okay, so this is just to show that if you don't have this side wall, then you have this mixture of bubble and not a complete air layer under the hull. Okay, so this is show you based on using CFD to show you the wall shear stress effect. So wall shear stress effect reduces with the presence of the micro bubble or air layer. Okay, so the more air layer underneath the hull, the lower will be the wall shear stress. So that's the thing they have to sort out. Yeah, have to try to cover as much as possible under the hull. But as I'm sure just now, by putting some sidewall. Yeah? Okay. So for our case, air injection ballast free system for LNG vessel, the solution that we propose here is that more with the ALDR method, yeah, producing the air layer, because it's more effective than the MBDR, the micro bubbles. As I mentioned, ACDR is not that popular with the owner, yeah, with the by making the empty compartment underneath the hull. Okay, so the objective here is for the research is to determine the total hull resistance. Okay, fitted with and without air injected for the free ballast system, and then to evaluate the role of the air injection to the ballast system and determine the contributing factors that contribute to the resistance or reduction of the resistance. So this is the methodology. So we follow based on this continuous. Okay. Okay, we have the outlet and inlet and outlet to consider, and then air injection. So basically, the inlet is at the bulbous bow, and outlet is at the stern. So this is the proposed concept for that we introduce air injected ballast free system. So you have the water from the bow goes into these pipes, then it goes into the ballast tank. Okay, and also air is injected before the water is released to the outlet. We inject air. Okay, so the outlet is a mixture of the air and water. This is the CFD method. So before we do the experiment, we have to study the numerical method first to see whether we are getting it right or not. So you use the ANSYS CFX for this. Even at that time we are still new with the CFX, but however now we use OpenFOAM. Because CFX you have to pay license. You still have problem paying the license, so now we have to opt for OpenFOAM. That means we have to have some lecturers specialized in this area running the CFD. So basically, it's just a numerical. To me, it's just like a virtual tank, running this thing in a virtual tank before you do it in a physical tank. So you have to set your boundary condition, use the solver like CFX. Yeah, I don't need to go to detail here. And you put something like a water is. You have the vessel inside this. So all this represent the part of the tank, right? Inlet and outlet water. So in the towing tank we tow the model, right? But since it's easier to flow the water, yeah, in using the CFD, it's the same thing, just relative movement between the model and the water, is it? Because for the towing tank it's very expensive to move the water, is it? It's cheaper just to tow the model instead of moving the water. Okay, so we have this hull, tank, wall, and so on, yeah. Injection inlet, then you use this K omega turbulence model. So with the CFD, actually we have to tune it, you know, this numerical model with the physical model. The result is the trend is there, but for comparison with physical, usually we tune it. So for the tuning of this CFX or CFD here, you use the K omega turbulence model. This is quite a common method used. Okay, so this is the grid. So they have to introduce a lot of this grid, yeah. So that the more grids you have, the more the heavier is the computation. So we have to use this what do you call that? High performance computer for that. So we are also planning to buy more high performance computer because we in the future we see that more of the CFD will be required. Even now our customer or client prefer us to compare, run both CFD and the physical experiment. Okay, because in CFD we can have better visualization than the towing tank. So we have a towing tank which is length of 120 meters. The length of the towing tank is 120 meters. It's quite for this is quite a big tank. The depth is 2.5 meters and the width is 4 meters. Okay, so this is the tank, actual physical tank. Okay, and the carriage speed. So as I mentioned, you have to tow the model instead of moving the water. More expensive to move the water of this size of tank. Then we make a model. So all these are made in-house in the lab. So to make this using gelutong wood. So this is the model of the LNG. Actually, it's the Tenaga class. But Tenaga class is not operation now. So it's the first vessel made for this. Okay, so the length is 280 meters. So we have the scaling about 80 scale factor, and in the tank the model is about 3.5 meter long. Breadth 41.6 in the model, 0.52 meters, and the draft is 9.76 or 0.12 in model case. Okay. So we have this model. So this model was done previously from previous research. To determine the resistance of this hull, because the last time the problem is this hull they have problem when it's maneuvering in the Suez Canal. So it was a maneuvering problem. So later on we use the model to study the resistance as well as the effect of this pre-ballast and air injection. Okay, so this is the tank. I think tank, yes. Now the tank. So this is the model setup. So you have the solid ballast here, and you can see all this pipe here that goes into the hull. Actually, this is the air pipe. So they have the air filter, and you have a compressor to produce the compressed air. Okay. So this again the tank. This is the protocol. So you have different test numbers, different speed for full scale, model scale, and also the fruit number. Okay. And then we also have different air injection pressure from 0.5 to 1.5 bar. Okay. Then we test 3 sets. Yeah. First, the bare hull. That means the original hull. And then we include the free ballast system. Okay, that water flows inside the ballast tank and goes in and out. And then we incorporate the air injection, yeah, to the pre-ballast system to reduce the increase in the resistance. So these are the results. So, so total resistance, yeah, this is how we plot the total resistance against float number. As I mentioned, yeah, the basis of the explanation is based on float number. But as I mentioned just now, we have to incorporate the skin friction based on Reynolds number, yeah, to the total resistance. So this is the bare hull resistance, and underneath here is the thick line. The thick line here is the bare hull, and then this dotted line above is due to the incorporating the free ballast system. As you can see here, the resistance increased very significantly with the free ballast system. And then we have air injection method. We have 3 results here. 0.25 B. B is the, what do you call it, bar. Yeah? So 0.25 bar. This is 0.5 bar and 0.75 bar. And you can see with the reduction of this air injection, it does reduce the resistance going back closely to the original bare hull. Yeah? So this shows that the air injection is very effective, yeah, in reducing the resistance. Yeah. Okay, so and then we study on the effectiveness of this air injection, based on the pressure that it produces, right? So because the pressure will affect the what they call the rate of flow of the air going into this water for the air injection. So you can see that at lower float number, it seems quite effective, yeah, in reducing the resistance. Okay, and then at higher speed, it seems to be less effective. Yeah? Okay, so that means this effectiveness of resistance also depends on your forward speed. Okay, so forward speed means this will be quite effective in reducing resistance. But for vessels that are using like slower speed, medium speed, may be effective, but higher speed maybe not so effective, yeah, with the air injection method. Okay. So this is the comparison we made with other researcher, you know, basically from Yanoa et al. And Tuan et al. Yanoa et al. Uses the micro bubble. Okay. Yanoa, okay. The Yanoa one is this one, black one, yeah. The thick black line here. That's Yanoa. And then Tuan is using the created small bubbles, yeah. Okay. And it seems that Tuan get a better, is it? Better, yeah? Tuan, yes, Tuan. Oh, Tuan is less, less. Created bubbles. Okay. So it seems here that using the ALDR method is better than MBDR, because this one use the MBDR, yeah? Tuan use the MBDR and Yanwa use the ALDR. And we also use the ALDR. So our result is better than the rest, than the one that we compare. So we are now thinking why we are better result. I think the thing is that because we have this pre-ballast system, this water moving as well in the pipe, and then as we introduce the air injection, the water just move with the air as well. It gives you the platform for the air to move. So this is what we think. I don't know what we think, but we haven't we've done any detailed work on this. So we hopefully in future we detail out why that our result looks better than the previous one, because the previous one, like Yanua and Tuan, they only use it for the behal. They were not researching free ballast system, you know. Okay, we do it because we want to reduce, you know. We have already the free ballast system, and then we introduce the air injection. Okay, so that may be a point that we can further study on the effect of this moving water as well as air injection. So this is the water volume fraction. Right? So you can see the water volume means how much water is in the volume. You see? So the top one with the red one is mean that is all is water. You know, red all is water. So this is a bare hull and ballast free system. Okay. The bottom one with the blue, all these blue colors are due to the air injection. You can see that now you have more blues than red. So I mean there is less water volume, and there is a mixture now with the air. Okay, and with this we can study on how much of the water volume fraction that is the optimum volume or volume fraction to introduce. Okay, if you introduce too much air, so it wouldn't be that optimal. Okay, in fact, it may increase the resistance as well. So this is the result showing the effect of this water volume fraction. You can see with the smaller water volume fraction, you tend to have better result. That means less water and more air here. You know? So okay, but when you have very smaller, more water, then you have less reduction. Okay. So this is the effect of the water velocity under the hull with the effect of this what they call air injection pressure. Yeah? So the red one shows you that the water goes faster, especially at the stern of the vessel. It may affect the rudder and propeller as well, performance. But that's another research that to do. This is the water fraction effect on the flow of water in the pipe. Yes, pipe. So with the pre-ballast system, the rate because the water goes freely, goes in. And then when you start to introduce this injection, it tends to give you some blockage effect of the water coming out. It tends to slow down the water. So this is what you need to study. Yeah. Okay. So this is water vessel ballast tank at operating approach number 0.19. Okay. Okay, before make any conclusion, this is an example of calculation, because we only at the moment study effect on the model, based on the model. So how do you predict that this powering estimate for the full scale? Okay, so this is the calculation, basic calculation using Excel. So we have the ballast-free system first. Okay, and then on the right side is ballast-free system plus air injection, for 0.5 bar pressure. So we can estimate the coefficient of resistance. These are the data we have: length, breadth, wetted surface area, velocity, fluid number. So for now, I just look into the one fluid number. This is around the design speed of the vessel, so 0.19. And this is the density in water as well in salt water. For the full scale, you use salt water, 1024 kilogram per meter cube. And then we also use the kinetic viscosity of the water, for the study on Reynolds number. So this is the kinematic viscosity. Then calculation of Reynolds number. This is important to determine the skin friction, because as I mentioned, skin friction using the ITPC 1957 skin friction, because it is a function of Reynolds number, not a Froude number. See? Then we can obtain the total resistance by measuring the resistance during the towing tank test. So this is the model result. And then we have to scale up this result to the full scale. Yeah? So the way we scale up, if we're using a coefficient of total resistance. So first we need to determine the coefficient of total resistance. Basically, you can get it directly from here. And then we can derive the coefficient of wave making. Yeah? So this is the total. This is the estimated using ITTC. So the balance will be the coefficient of wave making resistance. So this coefficient will be constant throughout, because this is based on Froude number. So we are running at the same Froude number. So all the coefficient making resistance will be the same. So from there we can get our what do you call that? The coefficient of the full scale, So we can know this one, okay, and then we can calculate for the ballast free. We can just calculate using the ITTC formula, okay, and then you can get the total, and then we can predict. We can calculate once you know the total coefficient of the resistance. We can get the what do you call the total resistance in terms of Newton. So this is for the free ballast. So this one is not a problem to predict. The problem here is how to predict it for the air injection. Okay, so the way we need to do is we have to, as I mentioned, we can use the same coefficient of wave making for this, for the model as well as for the full scale, with the air injection. And then with the experiment, we can determine the total resistance, 4.3 here. Okay, and then from there we can derive the coefficient of this skin friction, because we don't actually know, right? Because of the air bubble or air layer. So this one doesn't follow exactly the ITTC formulation. No. So we have to derive it using the total resistance that we got from the experiment coefficient, and then with the assumption that wave making resistance is constant coefficient, and then from there we derive the coefficient of skin friction affected by the air injection. Okay, so now we have to go to predict for the full scale. So the full scale, we just have to assume the ratio of the skin friction reduction due to air layer is the same both for model and full scale. So either the same, if it is 50% or 30% reduction, it will be 30% reduction in the full scale as well. So by using this assumption, we can derive the skin friction due to the air injection in full scale, because you know the coefficient of mechanism is constant throughout. Okay, then we can derive this one based on the ratio that we got from the model test, and then we just add up these two to get the total resistance coefficient, and from there we can derive the total resistance for the full scale. So with that, we can get the effective power. Effective power is just the total resistance times the velocity of the vessel. Okay, so we can get all this model scale, full scale with no air injection. Then this is the air injection, and we can now see the percentage of reduction. So for the model case, you can see that the reduction is 29.6%, right? But if you go to the full scale, you can see that the reduction is not 29.6. Now it's only 19%. Okay, so this is what the owner will be interested in, you know. Okay, so the 19%, we have to reduce it further, right? So at the moment, from what we know, the assumption here is about 7% of your effective power will be used to as input power for the air injection. So the net reduction will be just the 12%. But 12% is quite significant. Okay. So just imagine you start off without this free ballast system, just from the bare hull. Okay, we can get a reduction of your power by 12%, you know, by introduction of the air injection. Okay, so it seems quite promising in this using the air injection to reduce your power consumption. Oh yes. Okay. So like we go to the almost at the end, conclusion and future work. So the free ballast system, okay, you know that is increased the total resistance about average of 34% here. So for the free ballast system, the resistance is rated to be higher than the model. Okay, when you're operating at lower speed and lower at higher speed. Okay. So the use of air injection has reduced this free ballast system resistance by 1.7% on average. Okay, for air injection overall. Overall, when you do this, when you use the ballast system and then we use the air injection, so we get almost the same resistance that we had before. Before introducing the free ballast system. So the most effective injection pressure is the low pressure speed, about 0.25 bar, while at higher speed, 0.5 bar. Okay, so that means you have to really find the optimum compressed air to get to have this air injection. So if you use it too high, maybe it's only good for higher speed. You know? For the lower speed, should have a lower pressure. Okay. So these are the recommendations to use pump to enhance the flow of water. So that's another thing. Because to increase the flow, so it seems that with the air injection, it does affect the flow of the water in the pipe. So that's for the free ballast system. And then to relocate suitable air supply so that the ballast system can improve its performance. Okay, this is the position of this inlet outlet, especially the outlet. And then the water outlet configuration need to be explored for better system. I mean the shape of the outlet also need to be studied. So these are just to show you what are the other researchers has done, in terms of air injection. So this is from Wu and Wu in 2022. So they focus more on the shape of this. I don't know, is it shape? Yeah, maybe the outlet. Yeah, here. So they have these air holes, introduced so that you can get this injected air inside here. Okay, and then they have this tank, and then this is the tank with the water moving, Okay, so the model may be a smaller model, maybe not a towing tank. And they have this air supply, flow meter, air injection device, and you have the camera to have a look, the thickness of the layer and so on, like this, So this is from Feng, This is focus more on the outlet shape of the air injection outlet as it goes out there to inside the underneath the hull. So it seems that they claim that this using this nickel section, call it nickel, is a combination of actually two pipes to make this shape. So they claim that this is effective to reducing the drag. Okay. This is from Howe et al. 2019. So this is more on the looking at the shear stress. And they put some sensors here, and then also they measure the what they call the drag of a plate, in somewhere in the middle here, in the middle of the hull, so that they can actually get the exactly the reduction of the resistance on the flat plate due to the air injection. So this is from again Howe et al. 2019, looking at the different sidewall. They tried to put a sidewall to contain the air underneath the hull. Okay, and these are some of the results. So by changing the what do you call it? This is the air layer. Yeah? Looking at the air layer and see how effective this reduction in the resistance, by changing the sidewall, putting a sidewall, then they have a forward step and a rear step as well. Okay, this is given just now, the air layer thickness, using the flow rate, velocity, and the breadth of the test model. So thank you. That's my presentation. So next thing is the
Yeah, thank you very much,
yes.
Prof. Probably I need to on again my video. Just very quick. Okay. On Q&A, I've got a few questions. Hang on. Okay. The first one would be on the benchmarking of the results. So at this moment, the benchmarking is purely based on experimental and CFD.
Yes, yes, that's right.
The question here, they are more emphasized on the CFD. How you how the model been benchmarked, the result been verified, and you eventually concluding into the remarks.
You see, the way we do it, we compare the numerical with the experiment. Okay.
Right.
And the result of this CFD, usually we tune it, because there's a lot of turbulence model. You have to tune the model so that it goes as close as possible to the physical result. Because the physical will be the benchmark. You see, that's actually the they actually follow the physics of this phenomenon.
Any deviation at this moment in terms of percentage of bias and all that?
Yes, there must be a percentage difference. There must be a percentage difference. It depends on how much of the CFD can follow the physics of the situation. See?
Right.
So that is the benchmark based on between the physical and CFD. CFD is used after you do that what they call benchmarking, right, with the experiment, because experiment is very expensive to do. So the way to do it is that once you are sure that you have almost the same result as the experiment, then you do we call it parametric study. You change the parameters using the CFD.
Typically, how long for you to develop a good model in order for you to have good correlation with your CFD?
It depends on how complex the thing is. You see, there are a lot of features still, they are still doing it. You see, because there is a lot of these parameters still not understood. You see, like the shape of the outlet. Some people would some porous, or and there is some people say, oh yes, maybe the size of bubble could be affect, or the size of the outlet could be affecting it. So they are just studying it using both experiment and CFD.
So we say it is still continuous study, yeah?
Yeah, it's still continuous study, but I noticed some countries already implemented on a trial basis, you know, on full
Yeah,
scale.
that's the next question by another attendees. So far, is there any prototype of any vessel being tested?
Yes, there is already. There is already, but very limited. You know, very limited. Only the country where that can, because this full scale, the cost is much higher to do, right?
Obviously,
So
obviously.
country like Japan or US or China may have already introduced. I saw some of them that they have introduced this already, and the
But is it
result
on the
promising.
commercial basis based on your record, or is still based on
Not
prototype,
really
or still
commercial,
based on the
more on
trial version?
the experimental. Now, the more experimental. But I think in future maybe this will be more important, yeah, more because once you can 2050, right? We have to
Yep.
reduce all this by 50%, you know. So all this
Ah,
will be required, you know. But now maybe there's still, you know, because industry doesn't like to, you know, if they can get away without spending higher cost, they'll do it, right?
oh yeah, yeah.
So
Industry is
very
always
try.
thinking about the cost. Okay.
Mhm. But the method that we follow now is, I think, that's the easiest method. I mean, it doesn't disturb much of the system on the construction of the vessel, is it? Because here we assume
Right.
that the vessel has already been constructed, and this is
Right.
more like modification to reduce the powering of the vessel, or to
Yeah,
reduce the.
because from the finding we could see that there are a lot of benefit adopting this injection system. But the next, perhaps if you can share, is there at your end any cost estimation, perhaps? Okay,
Oh
that
no, no, no,
have been worked
like
out
that.
at your end.
No,
No.
you don't. Yes, yes. But I
Yeah.
heard that some of the consultant are going to the industry and proposing some system, you know, to
Right.
use the resistant using the air injection. So they may have the cost that we don't have. But if they are producing, there must be. I think there must be something practical, you know. Otherwise, the industry wouldn't have make that proposal, is it?
Yeah, yeah, definitely. If I spend 1 million, then I need to get return at least 5 million, my friend. As simple as that. Okay.
Unfortunately, we are from the university. We don't think much about that. We are
Okay.
looking at
Okay.
solving, introducing ways how to reduce it. Mhm.
Right. 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 Right.
We hope
Is there
any
any
company
other
wanted.
plan? Sorry, is there any other plan with regard to this study in the future where the industry could participate, or the industry or the
Yes.
industry could provide any input into it?
Mhm. So the thing is that we want to do more study on this, right? So that
Right?
means we need some research grant, is it, to continue the study.
Yep. Yep.
We need to get the grant. Either we got it directly from the industry, or we get it from the government.
Okay.
Uh, from the industry, maybe maybe the port use, you know, they have a lot of money, I think.
Okay. Right.
But we need to convince them. This is the way to go. Especially this thing, this IMO what do you call, regulation is being ratified by Malaysia. I'm a bit
Okay.
surprised that Malaysia is keen to ratify this. By
Yeah. Yeah.
2050,
Yeah.
50% reduction. I'm not too sure whether they regret it or not. But
Yeah.
that means,
Personally, I was involved into it as well last time. Okay.
yeah. Mhm.
Okay.
But it's good for us. That means they are now worried, how to solve the problem. So then our proposal for this method maybe will be more acceptable, either to get a government grant or industrial grant. But it must be under national interest, you see. So
Mm,
we are
mm.
planning to do this promotion, right? To show
Right.
to the industry that hopefully we can get support from the industry, and either we get it from the industry or from the government. But support from the industry is, to me, is quite crucial here, Mhm.
Okay. Okay. Perhaps that was the reason why we are calling you in. Okay, just to expose this. Then perhaps
Mhm.
yeah, since the question coming up from our attendees, so I presume that there are certain participants who are interested into this study as well.
Mhm.
Yeah, there's
But
5
hopefully, I think
questions.
the participant by industry understand the basic, what do you call it, the basic physics of this. in reducing the powering,
right.
especially in reducing the shear stress, friction and shear stress, and from there we can estimate how much powering reduction we can get from this system. So once if the industry is convinced in that, I think it's be easier for us to propose further research on this.
Right. Yeah, don't forget, if I could recall, we would have a site visit to one of the yacht fabricator probably next 2 months. So probably during our visit, we can we can follow up on this issue to them as well. Okay, if they're interested. Yep. What else is question? I did ask about benchmarking, prototyping, benefit adopting, yes, cost construction, and the study plan. So that basically about 5 questions that I received from the participant. And I have to reiterate again that the presentation material is available afterward, and then everybody can download from the system. Yeah. Last but not the least, is there any last word that that you wanted to share with us?
Just to say that the government has spent 30 million in building the towing tank. It's very expensive equipment.
Where in UTM?
So, yes, in UTM.
Okay.
So it's a pity if we don't use it, to solve problem like this. So
Okay,
we
this is
should
a part of
come up with,
part of your promotion, yeah.
yes, not just promotion. We are part of the, what do you call it? University is part of the government setup, for education,
Right.
and research. So university must produce, this is our function, right? To teach as well as to do research and development,
Right.
and especially if we can participate in improving the, what do you call it, the operation of the industry, especially in this ship operation. We're happy to do it. Otherwise, 30 million ringgit is a waste,
We
But
noted
anyway,
that. We noted that.
yeah, not really a waste. We have this industry coming to our towing tank for doing the model test. But we want, what we want is the more what do you call it, more requests from the industry, especially in the R&D part, you see.
Okay. Point noted. Yeah, seems there is no more question now. So 12:48. If I could conclude now, perhaps, Prof. On behalf of MNATD, IEM, I wish many thanks to Prof. Dr. Hadi Maimun. It is an honor for you for your presentation today, and as well as for all the participants for today. Yeah, for your time. Again, to all attendees, you could download the presentation material after this session. Last but not the least, please do support and keep up with IEM website for our subsequent activities. Right. Thank you very much, everybody, and we will meet you again in the next session.
Okay.
Thank you, Prof.
Thank you. Assalamualaikum and bye-bye.